Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson about thermoplastic and thermoset polymers. In the last lesson, we studied the properties and uses of synthetic rubber. We learned about some of the common synthetic rubbers, such as neoprene, butyl rubber, and styrene butadiene. Today, we are going to learn about the properties of thermoplastic and thermoset synthetic polymers. Are you ready to begin, students? We have discussed many different synthetic polymers during this unit, and we have learned if each is thermoplastic or thermoset. Let us learn a bit more about what it means for a polymer to have one of these properties. A thermoplastic is also known as a thermo-softening plastic, which gives you a clue about its physical properties. It is a polymer that turns to a liquid when heated and freezes to an extremely glassy state when sufficiently cooled. Most thermoplastics are high molecular weight polymers. Their monomer chains can associate in a variety of different ways, but they are all alike in that they can be remelted and remolded. Most thermoplastics are addition polymers. It is time for our first activity, students. We have studied many different polymers during this unit. Which ones were thermoplastics? Can you name any other thermoplastic polymers? Please take a few moments to list as many as you can.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I hope that you were able to list a lot of different thermoplastic polymers. There are too many thermoplastic polymers to list them all here. Some of the most common varieties are polyethylene, polypropylene, polystyrene, polyurethane, PVC, nylon, polybutylene, polyphthalamide, and the whole family of fluoroplastics. I imagine that you were able to name other polymers as well. Teacher, after the lesson, please review the students' lists and make sure that all of the polymers they named were thermoplastics. Thermoplastics are elastic and flexible above a certain temperature level. This level is called the glass transition temperature. It is the reversible transition in amorphous materials from a hard and brittle state to a molten, rubbery state. Each thermoplastic has a different glass transition temperature. Above this temperature, but below the higher melting point, most thermoplastics have crystalline regions that alternate with amorphous regions. In these amorphous regions, the polymer chains are like random coils. The crystalline regions combine with the amorphous regions to give a thermoplastic its physical properties. The crystalline regions grant strength and rigidity. The amorphous regions grant elasticity. If the thermoplastic is heated to a point above its melting temperature, the different regions begin to blend together and disappear. The viscosity level decreases without any distinct phase change. Let us see what you have learned, students. Please define the term glass transition temperature. Then briefly describe the properties of a thermoplastic that is between its glass transition temperature and its melting point. Do your best, and I will see you in a few minutes.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. How did you manage with this exercise? The glass transition temperature describes the temperature above which a thermoplastic goes from a brittle to a rubbery state. When it is between its glass transition temperature and its melting point, a thermoplastic has both crystalline and amorphous regions of polymer chains. It is the combination of these regions that give thermoplastics their remarkable properties. Do your definitions agree with mine? Great job, students. You have learned the basics of thermoplastic polymers. Thermosets, also called thermosetting plastics, are very different from thermoplastics. Thermosets are usually liquid or malleable prior to curing. They are either used as adhesives or molded into their final forms. Others are used as solids, like the molding compound used to manufacture semiconductors and integrated circuits. The curing may be done through heat, through chemical reactions, or through a process of irradiation. After the thermoset has been molded, energy or catalysts are added. This causes the molecular chains to react at chemically active sites. The molecules are linked together into a rigid, three-dimensional structure with many crosslinks. The curing is irreversible, meaning that the polymer network becomes infusible and insoluble. Because of their cross-linked network molecular structure, thermosets are generally stronger than thermoplastics. They also have a higher melting point, so they are better suited to high-temperature applications. However, they are also more brittle. In addition, they cannot be recycled, except as packing material. Students, we have studied 2 thermoset materials during this unit. Do you remember what they were? Please take a moment to write down your answer. When you have finished, write down the advantages and disadvantages of thermosets compared to thermoplastics.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello again. I am confident that you remember which thermoset we have studied. The answers are Bakelite and Perspex. Their rigid, cross-linked molecular structure makes them both stronger and more heat-resistant than most thermoplastics. However, they are also fairly brittle. They cannot be reused after they have been molded and cured. If those were your answers, great work. Some other examples of thermosets are fiberglass, polyamides, melamine, epoxy, and vulcanized rubber. Today, we have learned about thermoplastics and thermosets. We have studied their properties and the chemical causes of those properties. We have also named several examples of each kind of plastic and learned the definition of a glass transition temperature. That is all for this lesson. Until next time, thank you, teacher. Thank you, students.